Hello and welcome back to Summer Work Help for Calculus 1. This video we're going to be taking a look at question number 3. The directions here say, express in simplest radical form. So we'll just dive right into it. So 3a. So for 3a, we have one term, 27x to the 6th. It's a product, but it's one term. And that one term is being raised to a fractional exponent. So notice that for this problem, the fraction is 1/3. So writing this out is not strictly necessary, but when you have an exponent that is 1/3, that is the same thing as the cube root. So that's how we indicate a cube root. If you're talking about a square root like that, then x is 1/2. And notice that with a square root, you don't write the 2, right? Because square roots are by far the most common roots. So if there is no number there in the top left, then you can kind of assume it's a 2. And every single time you've seen a square root, there's been an invisible 2 there. But this is not a 2, this is a 3. This is a cube root. So as we're going through this process, some of you may find, maybe there's an easier way to go about it or kind of a simpler way. The way that I approach these kinds of problems is I look to express the different factors and the different terms in sort of like groups that will sort of allow me to pull out numbers from underneath the root. So here's what I mean by that. For this problem, we're dealing with a cube root. It's 1/3. So what I'm kind of looking for is can I express any of these values as essentially as something cubed? So I'm going to leave everything underneath the cube root for a second. Or if you'd prefer to leave it as the 1/3, that's actually also fine. You don't have to write it as a radical form just yet. You could leave it as the 1/3. But I'm going to take each of these factors here, and I'm going to try to see can I sort of chunk them in essentially in groups of 3, something times something times something. So the first number I have is 27. Well, this actually works out quite nicely because 27 is 3 cubed. Right? Those are equivalent statements. So 3 cubed is 27. Right? And that's actually going to work out very nicely. And then looking at the x to the 6th here, well, I notice that I can rewrite my x to the 6th as x squared to the 3rd power. So this is kind of a variant of something that we saw in question 1. It's actually kind of like going backwards. But when I have x to the 6th, 6 is 2 times 3, and when I have a power to a power, I multiply. So x squared to the 3rd power is in fact x to the 6th. So what I have here is I have something to the 3rd power times something to the 3rd power. So what I can do is that 3 cubed, when I pull it out in front of the cube root, I'm left with just a single 3. But notice it's no longer underneath the cube root, right? It's just 3 kind of by itself. Likewise, I have x squared to the 3rd power. So when I pull that out from the cube root, I just have a single x squared. And then the only thing that's left underneath the cube root at this point is kind of this placeholder of a 1, because I was actually able to pull everything out from the cube root. I was able to pull the 27 out and it became a 3. I was able to pull the x to the 6th out and it became x squared. And so the only thing that's left underneath the square root is this placeholder of a 1. Well, the cube root of 1 is just 1. So that just kind of goes away. And so my final answer for 3a is actually relatively simple, even if maybe the process getting there wasn't so simple. But my final answer is just 3x squared. So it actually worked out fairly nicely for 3a, because sort of everything involved underneath the cube root could be expressed as a cube. And so when you pull it out from underneath the root there, each bunch has 3 of them, so you're left with just 1, but the root essentially goes away. So final answer for 3a is 3x squared. There's alternative ways to approach that problem. So if you got to 3x squared, but you thought about it differently, again, the chances of you lucking into the correct final answer, are pretty small. So if you have another way of looking at that problem that gets you to 3x squared, then great. All right. B. So B, similar to A, I have one term. I have it's got 2 factors in it, but I have one term of 50x cubed, and that's being raised to the 1/2 power. So as we kind of alluded to in 3A, when you have something that's being raised to the 1/2 power, that is the same thing as the square root of that thing. Now, there is an invisible 2 right there, okay? That 2 is there, but don't write it, because with a square root, you assume that the 2 is there when there's no number there, you can assume it's a 2. So, I want the square root of each of these factors. So, what I want to do is I want to take each of my factors, and I want to sort of write them as something squared. All right. So I noticed that with the number 50, well, the square root of 50 is an irrational number, right? So unlike A, with B, I'm not going to be able to pull everything out from underneath the square root. We're still going to have things under the square root when we give our final answer. And that's okay, because that's called simplest radical form. But I want to try to get as much out from underneath the root as possible, because it's just makes things easier down the road if your roots are as simple as they can get. So I noticed that with 50, I can write 50 as 25 times 2. And the reason why I want to write it as 25 times 2 is because 25 is a square number. 25 is 5 squared. So sort of my goal here is to try to think about, all right, what is the factor of 50 that is the largest square number that goes into 50? Well, there's no square number above 25 that goes into 50. 36 is a square number but does not go into 50. 49 does not go into 50. And then obviously anything above 50 doesn't go into 50. So 25 is my largest square root. That's why I'm writing it the way that I'm writing it. And then continuing on here, I have x cubed. And just like with the 50, I want to write that x cubed as, something. I want to write it as bunches of 2s, essentially. Well, I can write it as a single bunch of 2, and then I have like 1 left over, like that. Okay. So it certainly looks like I'm making this problem more complicated, and sometimes that happens in mathematics. You kind of have to make it more complicated before you ultimately make it in its simplest form, right? So we're obviously not done here, because we're just kind of breaking things up and making things a little bit more complicated. But now we can start to simplify this. When I pull the 25 out from underneath the square root, well, what's the square root of 25? The square root of 25 is 5. Right? So essentially what's happening is one of these factors of 5, it's 5 squared. One of them kind of like goes away, I guess, because of the square root, and I'm left with just a single factor of 5. Now the 2, there's not much you can do about that 2, right? That 2 is kind of trapped underneath the square root, and we're just going to kind of leave it there for a second. Likewise, I have the square root of x squared. Well, the square root of x squared is just x. We saw that in question 1. So when I pull the x squared out, I'm left with just a single x. Notice it's no longer under the square root. Now I also have the other factor of x, but that's just x to the first. So that's kind of also sort of trapped underneath the square root, and you can't really get it out of there. So now I'm going to write whatever's left, right? Whatever I was not able to pull out from underneath the square root. So the 2 was kind of trapped under there, and the x was kind of trapped under there. And then there's not much more you can do with this problem. We've pulled out as much as we possibly can from underneath our root, and there's certainly nothing else that we can simplify. So our final answer for 3b is 5x root 2x. I've successfully pulled out as much as I can from underneath the root, and anything that I can't stays underneath it, and that's my final answer. And it does say express your answer as simplest radical form. In another context, right? I'll do this in red, I guess. In another context, you might want to write it like this, right? And just kind of write it as a fractional exponent again. And those are mathematically equivalent, but it does say simplest radical form, so you don't really want, in that case, you don't really want fractional exponents. So even though this is mathematically equivalent, it's not wrong, but I wouldn't write it, right? So that's not simplest radical form. So I guess I'll erase it. But just know that it is quantitatively the same thing. All right, 3C. So for 3C, again, we have one term. So 16x to the 9th, y to the 8th. It's kind of all mushed together. There's no addition or subtraction, right? That's when I say it's one term. You can have like 20 factors, but if it's all one term, it's one term. So I have one term, all smushed together, and I'm raising that to the 2/3 power. Again, this is a problem where it is entirely possible that you would have a different approach to this problem. And again, I would say that if you get the right answer here, if your final answer matches the one that we're going to get right now, then go with it, because the chances are of you lucking into the right answer are pretty small, okay? But I'm just going to kind of show you the way that I would solve it. Maybe you have an easier way, and if so, then that's great. So the first thing I'm going to do, well, I'm going to kind of do two things at once. Maybe that's a good idea, maybe it's not, I don't know. What I'm going to do is, first of all, notice that in my exponent, my denominator is a 3. Okay, right there. It's a 3. Because my denominator is a 3, it means that ultimately at the end of the day, what we have here is we have a cube root. Okay, so sort of the denominator of your fraction sort of tells you what type of root you're dealing with. If it's a 2, it's a square root. If it's a 3, it's a cubic root. If it's a 4, it's a quartic root, and so on and so forth. So we have a cube root, but notice that unlike parts A and B, for C, my numerator is not 1. My numerator is now 2. So what's going to happen is that 2 is going to distribute to all 3 of my factors. So it's going to distribute to the 16, it's going to distribute to the x to the 9th, and it's going to distribute to the y to the 8th. So you're more than welcome to use your calculator, right? So 16 squared is 256. Okay, I'm just distributing the 2 to the 16. X to the 9th, I have a power to a power. So this is x to the 18th. And then I have y to the 8th. So again, I have a power to the power. So this is y to the 16th. Okay, so again, I kind of did two things there. I rewrote the denominator of my fraction in my exponent. That's the root. And then the numerator, I just distributed to everything. And so I squared everything. All right. So we got a cube root. So because I have a cube root, I want to try to identify what is the largest. So with the 256, the step that we're about to do right now, in my opinion, is probably the hardest part of this problem. Because what I want to do is I want to figure out what is the largest cubic number that goes into 256. So I'm just going to do a little kind of a little sidebar over here. 1 cubed does not help because 1 cubed is 1. So if the largest cubic number that goes into a number is 1, that doesn't really get you anywhere because you divide by 1 and nothing changes, right? So if that is the case, if that's the largest cubic number, then there's not much we can do. 2 cubed is 8. All right. So now I'm not gonna pull up the calculator because you can kind of do this on your own. If you do 256 divided by 8, and we get a whole number, we get 32. So what that means is 8 works. 8 is a cubic number that goes into 256. Okay. So 2 cubed is promising, but we don't just want any cubic number, we want the largest cubic number. So I'm actually going to keep going and see, all right, can we get maybe a larger cubic number that goes into 256? So then we've got 3 cubed. Well, 3 cubed is 27. I'll tell you right now, 256 divided by 27 is not a whole number. It's 9.48, et cetera, et cetera, et cetera. So that's no good, because 27 does not go into 256. So the 27 is not a factor of 256. So 27 is cubic, but it's not a factor of 256, so that's no good. 4 cubed is 64. And 256 divided by 64 is 4. So that does go into 256. And I'll tell you right now, if you keep going, like if you were to say try 5 cubed and get 125, that doesn't work. 6 cubed is 216, that definitely doesn't work. And then once you hit 7 cubed, which I think is 343, now you're above 256. That's obviously not going to work, right? So sort of our winner here, right, the largest cubic number that goes into 256 is 64. And I'm going to write that as 4 cubed. All right, so the 64 that is a factor of 256, I'm going to write it as 4 cubed. And like I said, when you take 256 and divide by 64, you're left with a 4. So I'm just going to leave it. All right, so I have this kind of this cluster of 4 times 4 times 4, which is 4 cubed, okay, and that's great. I'm looking for clusters of 3. And then I happen to have another 4, but that other 4 is kind of, it's just going to be stuck there, so I'm just going to leave it. Times. In my opinion, actually, the rest of this is actually easier than what we just did, because I have x to the 18th. So I want to write that as, I want to try to get as many bunches of 3 as I possibly can out of 18. Well, 3 goes into 18 6 times, which means if I express this as x to the 6th, and then I raise that to my 3rd power, well, there's that cluster of 3 that I'm looking for, right? I have 3 clusters of x to the 6th. I have x to the 6th times x to the 6th times x to the 6th, and that's great. And I actually used up all of my x's, so we're done with that term. Then we've got y to the 16th. So y to the 16th, I want to say, all right, again, how many clusters of 3 can I sort of get here? Well, if I express y to the 5th to the 3rd power, well, y to the 5th to the 3rd power, that's y to the 15. So I'm able to sort of cluster 15 of them into these groups of 5, so y to the 5th times y to the 5th times y to the 5th. But then I have this sort of this extra y, because it's y to the 16th. Okay, because 3 does not go evenly into 16, so we would expect there to be kind of this like remainder, this sort of this thing that's left. All right. Now I can start pulling stuff out. So the 4 cubed, when I pull the 4 cubed out from underneath the cube root and the 3 cancel, and I'm left with just a single factor of 4. And again, this is key. Notice that I'm no longer underneath the cube root because I pulled that 4 cubed. I pulled it out from underneath the cube root, and I'm left with just 4. All right. The other 4 is kind of stuck, so we're going to ignore it for a second. Then we've got x to the 6th raised to the 3rd power. So when I take those 3 clusters of x to the 6th and I pull them out from underneath the cube root, I'm left with just a single cluster of x to the 6th. All right, so the cubed and the cube root cancel, and I'm left with just x to the 6th. And then I have these 3 groups of y to the 5th. I have y to the 5th times y to the 5th times y to the 5th. So I have y to the 5th cubed. And when I pull that out from underneath the cube root, I'm left with just a single cluster of y to the 5th. So that's as much as I can pull out from underneath the cube root. Now I wasn't able to pull out everything. So I've still got a cube root term. Okay. So I've got the single 4 that we weren't able to sort of get rid of. I was able to pull out all of the x's. So there's no x underneath the cube root. But then there's this kind of this lonely y. It's going to hang out with the 4. So the 4y is kind of still trapped underneath the cube root, but everything else I was able to pull out from underneath it. And again, what you're trying to do here is you're trying to pull out as much as you possibly can from underneath the root. You want the root to be as simple as possible, and you want the coefficient to have as much stuff in it as you possibly can. So our final answer is 4 x to the 6th, y to the 5th, times the cube root of 4y. And that is our answer in simplest radical form. And again, if you were able to get that answer using some different method, maybe you did the cube root first and then you squared or whatever, that's our answer. All right. 3D. Now, here's what I'll say about 3D. If you're kind of struggling with some of the earlier questions, if you're struggling, like hopefully A makes sense. A, I think, is relatively straightforward. B is, B is not that bad. It's a square root. Hopefully you can get B. C was a little bit more complicated, right? But if ultimately at the end of the day, if you understood C, I think you're in a pretty good spot. D, just by looking at it, you can tell D is a little complicated. So maybe D is a little bit of an extension question. So, if you're maybe short on time, maybe if you waited till the last minute, you're kind of short on time, or you're just kind of, your brain is already kind of melted. If you don't get D, it's really not the end of the world, right? And again, there could also be multiple ways of getting D. I will show you how to do it. But if you're kind of hanging on and just getting C, you're probably in a good spot with this. But like I said, I will show you how to get this problem. So for D, this time we've got, well, I guess technically this is still one term, but we've got one term that's got a couple of different exponents on it. So we've got a kind of a lot going on in this problem. What I'm going to do is I am going to, for D, I think D might be a good opportunity for us to maybe see a slightly different way of approaching this. For D, I'm actually going to look at each factor in my first exponent here. So we've got the 4, we've got the x to the 6, and we've got the y to the 10th. And remember that when you've got a product like this, you can just sort of distribute your exponent. So we can actually just distribute the 3 halves as an exponent to the 4, to the x to the 6th, and to the y to the 10th. So let's just see what happens when we do that. When you take 4 and you raise it to the 3 halves power, I'm going to do this maybe as a sidebar. When you have 4 to the 3 halves, well, remember, the denominator tells you have a square root. So the square root of 4 is 2. So that 2 in the denominator means you want the square root of it, and the square root of 4 is 2, and then you want to cube the result, which is 8. So my first term here, that 4, when I raise it to the 3 halves power, becomes an 8. And because I get a nice round number, I'm just going to leave it like that. And if you take your calculator, if you do 4 to the 3 halves, assuming you type it correctly, you should get 8. For the x to the 6th, again, you can distribute the 3 halves, and I have a power to a power. So what this means is I have x to the 6 times 3 halves, Well, 6 times 3 is 18, and 18 divided by 2 is 9. So it's just x to the ninth. That is 3 halves of 6 is 9. Likewise, I have y to the 10th, and I'm raising that to the 3 halves power. So I have a power to a power, so that means I can multiply. So 10 times 3 is 30, and then half of 30 is 15, so this becomes y to the 15th. So my first half of this term simplifies rather nicely. Times. All right, I've got the second half. So now this second part of the term, everything's being squared. Okay. My numerator, I have a fraction here. My numerator says I have 4 to the 0.5. Well, 0.5 is 1/2. So 4 to the 0.5, that's a 5. 4 to the 0.5, that's 4 to the 1/2, which we just said is the square root of 4, which is 2. Okay. So that 4 to the 0.5 is a 2, but then we're squaring it. We're squaring what, this piece is 2. And I square it. So I square that 2, and I'm left with 4. Another way of looking at that is if you just take your exponent and distribute. If you distribute the 2, well, 2 times 0.5 is 1, and 4 to the first is 4. So no matter how you look at it, you get 4. And then I have x to the third to the second. So we've seen this now several times. When you have a power to a power, you multiply, just like that. Over, I have 9 to the 0.25. And that's getting, and that whole thing is being squared. It's going to get raised to the second power. A couple different ways you can look at this. Probably the easiest way is probably just to distribute your exponent first, because 0.25 times 2 is 0.5, which means it's 9 to the 1/2 power, and that means it's the square root of 9, and the square root of 9 is 3. So at the end of the day, that all just simplifies to a 3. All right. That's the hard part of this problem, okay? The rest of it, we're just going to clean this up. 8 times 4 is 32. So I'm just going to multiply I'm looking at my numerator right now. So I have 4, because this is really like over 1, right? So I have 8 times 4 is 32. I have x to the 9th times x to the 6th, which means I add my exponents. So this is x to the 9 plus 6, which is 15. And then I just have y to the 15 over 3. And 3 does not go into 32. All right, 32 is, 32 is even, but you could still have an even number that goes into 3. Anyway, 3 does not go into 32. It goes into 30, goes into 33, it does not go into 32. So I can't really simplify that any farther, and so that is my answer for D. Again, as I said at the beginning of this section here, if you can get A, B, and C, but if D tripped you up a little bit, you got a lot going on in D, so don't feel too bad. If we encounter anything like this during the year, we can revisit it, obviously. But for right now, I'd say as long as you get A, B, and C, you're probably in pretty decent shape. But I would encourage you to take a look at D and see, sort of does it make sense? So that's D. So again, I'll zoom out here, and those are all of our answers for question number 3.